All right, number 15, which of the following is the graph for the function? And they've given us y equals 1/2 times quantity x plus 1 to the fourth plus 2. And we have four different options, A, B, C, and D, and we are asked to determine which of the graphs here, shown A, B, C, or D, is the graph of this equation. And so we're going to use our knowledge of vertical translations, horizontal translations, and we're going to talk quickly about something new that we haven't looked at on this practice test yet, and that is the idea of a vertical shrink or a vertical stretch, depending on what's happening with the coefficient out front here. All right, but first things first, right off the bat, we can go ahead and eliminate one of these four graphs. And because graph A here is opening down, notice that graph B, C, and D are all opening upwards, but graph A opens down. And the only way that we could get a graph that opens down would be for this coefficient here, this leading coefficient, would have to be a negative. We would have to have a negative 1/2 for the graph here to open down. But that's not the case here. We have a positive 1/2. And so right away we know A can't possibly be our graph because we have positive 1/2. And in order to open down, we would need a negative of some kind. So we can eliminate A. Now that leaves us with B, C, and D. So now we've got to start using our knowledge of, as I said, vertical and horizontal translations first, and then we will look at vertical stretching and vertical shrinking in just a second. So recalling what we learned earlier, we know that horizontal translations, that means left and right movement on the x-axis, occur inside the set of parentheses here, and we always do the opposite of what's shown. So here we have a +1, which really means we're going to move to the left 1 unit. All right. And here on the end, we have a +2. This is our vertical translation, the up and down movement on the y-axis. And this indicates that we're going to be moving 2 units up. All right, so let's take a look at graphs B, C, and D. We want to look for a graph that's moved to the left 1 unit and that's moved up 2 units. And we can see that, well, it looks like all three of these graphs have moved, haven't they? If we start at the origin, move over to the left 1 unit and up 2 units, well, that graph B certainly fits. Again, graph C, if we start at the origin, move left 1 unit, up 2 units, graph C fits that characteristic, and graph D, I think, is also going to fit, right? Start at the origin, move left 1 unit, move up 2 units. So again, graph D also meets those vertical and horizontal translations. So this isn't really helping us much in this particular case because all three of our remaining choices have all moved to the left 1 unit and up 2 units. So now we've got to start using additional information. And that's where this vertical stretching and vertical shrinking comes into play. So vertical stretching and shrinking occurs based on what the coefficient here of this first term is. And we can see here that if that coefficient, and we usually refer to this coefficient as A, the letter A as an apple, if that coefficient is greater than 1, then the graph is going to have some sort of vertical stretching. And you can think of vertical stretching as the graph getting skinnier. You're stretching it out, so it's getting skinnier. If, however, this leading coefficient here, this A coefficient, is between 0 and 1, so 0 is less than A, less than 1, then the graph is going to shrink. So you can think of the graph as getting wider, getting a little fatter, if you will. All right, so we have graph B, graph C, graph D. Again, it's maybe difficult to tell, well, is this graph getting fatter? Because we know our graph is going to be shrinking because 1/2 is definitely between 0 and 1. So we would expect our graph to be getting fatter. But it's difficult to tell. Well, is B a fatter graph? Is C a fatter graph? Is D a wider, a fatter graph? Well, who knows? It's hard to tell, right? So we have one option left to us, and we're gonna solve this analytically, which is to say, let's see where this graph crosses the y-axis. All right, and to do that, we know to find the y-intercept, we're going to plug in 0 for x and evaluate, right? So let's take what we have, y equals 1/2 x plus 1 to the 4th plus 2. We want to know where this graph crosses the y-axis at. And so in order to find the y-intercept, we're going to plug 0 in for x and solve for y. So that gives us y equals 1/2, plug 0 in for x, so 0 plus 1 to the 4th plus 2. Let's clean this up a little. Y equals 1/2 times, well, 0 plus 1 is just 1 to the 4th plus 2. Again, still cleaning up. 1/2 times, well, 1 to the 4th is just 1 plus 2. And I'm going to move this over a little bit and maybe shrink it. All right, and we'll pick up over here. So 1/2 times 1 is 1/2, so we have y equals 1/2 plus 2. And we know when we add and subtract fractions, we need a common denominator. And right now we can rewrite 2 as a fraction, 2 over 1. And if we have a 2 and a 1, we know our common denominator will be 2. So we've got to multiply this 1 by 2 in order for it to be 2. But whatever we multiply the bottom by, we have to multiply the top by. So really we have 1 over 2 plus 4 over 2. And now that we have common denominators, that denominator can just move over, that common denominator can move over, and we can then go ahead and perform the indicated operation with our numerators. So 1 plus 4 gives us 5. So when it's all said and done, y equals 5/2. So when the x is 0, the y is 5/2. And if you convert 5/2 to a mixed number, you'll end up with 2.5. So let's see if any of these graphs that remain, B, C, or D, cross the y-axis at the point 0, 2.5, or 5/2. And I'm going to zoom in as far as I can. Oh, that's really far, but that's good. To see whether or not any of these cross at the point 0, 2.5. All right, well, B is a pretty good contender. We can see we have 1 here. Let me label. So if that's 1, ooh, that's going to write really big. Let's see. I don't think I can make this pen any smaller. Let's see. If that's 1, 2, 3, we can see that the y-intercept appears to be 2.5, which is what we're looking for. Oops, too far. All right, let's look at graph C and see where it's crossing. Well, again, we have 1, 2, 3. We can see that our graph appears to be crossing, graph C appears to be crossing at 3, maybe a little more, maybe even 4, but definitely not crossing at 2.5. So we can go ahead and get rid of graph C, and let's look at graph D. Well, again, we can see if this is 1 and 2, we can see this graph is crossing at what appears to be 2. Again, not 2.5, which is what we're looking for. So we can exclude D, and then that remains, or leaves rather, graph B as our only option as being the graph. So we'll say graph B, and I'll try to zoom out a little bit. And so there we have it. So for number 15, we're going to say graph B. We used our vertical and horizontal translations to kind of help us. We used the vertical stretching, vertical shrinking based on the coefficient A here to kind of help us. And then finally, we had to solve for the y-intercept analytically by plugging in 0 for x and then solving. And ultimately, that was what really helped us to determine whether it was B, C, or D. And so graph B, number 15, is our answer. I will see you at graph, or rather question number 16.